This is joint work with my colleagues, Olivier, Nicole, and Nicolas Osborne from Tarides. So to put you into the right mindset, my younger colleagues, oops, this is working well, would envision, well, some of this worked as follows. Slightly more serious. As Casey has presented, with OCaml 5.0, we get domain parallelism, which is very nice. It's still hard to write parallel and concurrent code, and it's hard to test it because of this inherent non-determinism. So this work is indeed a couple of libraries that I'm hoping that someone else could benefit from as well, and a bit of a shakedown of at least parts of the standard library under parallel. Example. So this is, well, as much as I could fit on one slide, testing selected operations of the standard lib hash table module. At the top there, you'll see, okay, we need to tell the library what is the type of the thing, the system under test. We choose somewhat arbitrarily chars and ints for the two type parameters. We need to describe how to set up that system, and if you need to, well, how to clean up after it or take it down. And then, well, exactly which operations do we want to test? And so we specify them in this C-types-like manner with a name, the actual value, and then a combinated signature describing the signature of each operation. And then, well, perhaps less importantly, in an attempt to be pedagogical for the alpha and the gamma here, I named them A and B, and I choose a couple of, oh dear, a couple of generators for those. Oops, yes. This is working well. All right, so let's see. Well, that's annoying.
Just don't press any buttons.
You can advance slides using this clicker.
Yes, except now was when I was hoping to do the demo. Oh dear. All right, so if you try to run something like this, and yes, brace yourself for a catastrophe.
Can you make the font larger?
I can try to. You get something like this. So we asked it to run 10,000 tests. In the fifth one, we found something that failed. Then there was some shrinking steps, and then a printout. So what are we looking at here? Well, it reports, if you start initializing the empty hash table, and then you spawn off two domains, and then it turns out it's enough to do the same thing in both domains. We do hash table add, and then length afterwards. Down here, you'll see the same thing, but annotated with the return values from those calls. And the library is saying, I couldn't find a linearization, a sequential interleaving of the results that I've observed by doing so. So, well, how many ways can you interleave something like that? Well, we could do an add first and then a length. Well, if we start with the empty hash table, add one thing, ask for the length. Well, one sounds plausible, right? If we then do another add, well, we have this OCaml hash table shadowing, where we have one entry shadowing the other, but by the semantics of the hash table length operation, that returns 2 if you do so sequentially. The other possible interleaving could be add, and then length, but then that should give 2, and that's not compatible return values either, right? And so because of the symmetry, I don't think there, well, it's early, and I didn't get enough sleep, but I don't think there are other interleavings. That's excellent. It's barely 10 o'clock. Did we already find a bug in the OCaml standard library? No, no. So this is a very nice and well-oiled hash table implementation, which has worked well for 25 years sequentially. We know it's not going to work as well if you just use something which was designed for sequential use and use it under parallel, and so you need to protect it. But it sort of nicely illustrates, I think, that this can find something. Yes, this was the backup slide where I have something like that, and you'll notice that. So this is randomized, but different seeds, at least in this case, you tend to discover the same things. So underneath the hood, if we scratch the surface a bit, there will be a sequential prefix that's the same sort of shape. Then we'll spawn 2 domains and then do some arbitrary commands in parallel. And the inputs to each of these calls will generate arbitrarily. And then by doing so, we'll also test random combinations. Yes. As I explained for the example, we record the results we observe from the parallel behavior, from the parallel interpretation. And then secondly, we perform this search through all possible sequential interleavings. It's enough if we just find one sequential interleaving that confirms the behavior. But if we can't find any one, well, the second phase, the test case reduction or shrinking, kicks in. Yeah. So this kind of testing is very much non-deterministic. So we'll use some good old tricks from the QuickCheck literature, like repetition to, pardon the expression, but make it more deterministic. Increase repeatability, if you will. Similarly, we tried, to start off things once they are spawned roughly simultaneously to avoid a situation where the first one is already done by the time the second one begins. Things like that. Yes. All right. So if someone comes up to you with a smirky face like this and a computer that works as well as this and tells you that those linearizability tests, they're passing now, you should take it with a grain of salt. It tests that things that are that we try out in parallel has some linearizable explanation, but of course that's not the same as being correct. So for your pleasure, I've here cooked up an example satisfying that, which I think you would agree that's probably not the implementation that you would want. All right. So how can we then test intended behavior, Jan? I hear you ask. Thank you for that question. So again, looking in the QuickCheck literature, there are good ideas there. And one is to use sort of a model-based testing. So the idea is, well, to express really the semantics, but we use a nice nice pure functional meta language called OCaml to express the semantics of these operations. And so we'll write two interpreters, one where we interpret these arbitrary calls over the actual system under test. This is black box testing, so this is the first line there with the black boxes. And secondly, well, we'll do it over our model here. And how do we model the internal state of a hash table? Well, I don't have time for a lot of thinking here, so well, let's use an association list. So the empty association list here models, well, the empty hash table. When we add an element to the imperative hash table, well, something changes inside the black box, and we'll express how the model develops. So these first operations, add, return unit. So there's not much to compare, right? But at least length, that returns a good old integer. And so we can compare, the integer we get back from hash table dot length, is that the same as our length operation over our model, and so on and so forth. All right, so this requires some more code, some more boilerplate. So I'll just briefly walk you through what's required. Again, a description of what's the system, the type of the system that we're testing, how to set it up, how to tear it down, what's the type of this model that models the internal state. We need a good old algebraic data type expressing, well, what operations can we perform here, and then we have a generator. So this is perhaps the first thing that is not entirely boilerplate. So the intuition for it is as follows. If we are handwriting a unit test for something like a hash table, wouldn't it be natural to have something where we add a key, say A, and then later remove that same key A, or look it up or something like that? Shouldn't be entirely unreasonable. Well, how do we then do something like that in our arbitrary tests? Well, we can skew the generator if we parameterize it by the state, the model, and then say, okay, well, if there is something to choose from with 50% chance, I'll choose one of the previous keys in the hash table. Otherwise, I'll generate something fresh. Yeah. And then, well, I said two interpreters. One interpreter here, well, symbolic add, we interpret by calling hash table.add, similarly for remove, and then wrap things nicely with some type safe combinators. We'll need to describe what's the initial state of our initial state of the model, and then a state transition function, a pure state transition function that expresses how the model advances for each of these commands that we want to test. And finally, there's a pre and post condition function. We don't use preconditions here, but for post conditions, we then check, that result we got back from run up there, does that agree with what, so for the simple example is the length one, does that agree with the length of our model in this case? Yes. So if there are people who are in the audience who have experience with state machine testing in QuickCheck, QuickCheck for Erlang, or Hedgehog or ScalaCheck or any of these other ports, and say, dude, this is old hat. Great. That's precisely the intention. This is sort of proven technology. And well, now that we have domain parallelism coming, this was exactly the intention of doing something which has not a lot of surprises.
You have to wrap.
All right. So when you do something like that, you can run these model-based tests both sequentially and parallelly. So the parallel one shares the same kind of skeleton, sequential prefix, blah, 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 and then you get a similar, yes. So we are doing something like that to give the standard lib a good shake. We are not quite there yet, but we are getting there. We've also made some tests for both domain slip and log free. We have managed, after some axe sharpening, to find things. Yes. While doing so, I admit, at some point I have run out of hair to scratch on my head. So I have good colleagues in KC and Tom Kelly and Angon, who can then step in and knows the new runtime much better than I do. But I think that KC would agree that this one was the first one that really had our scratching our heads. All right. Yes. Not everything fits nicely with this format, but there are also other fun surprises we've had. Yes. We're building on a lot of literature within QuickCheck. The skeletons, this kind of approach is I consider it sort of best practice within the QuickCheck community at least. So it works well for Erlang, so it might work well for us, and it turns out it does so. Yes, that kind of DSL signature, we didn't come up with that. Other people have done that. Yes. Yes, and of course there are other efforts in this community, but I'm running out of time here. All right. Overall, I hope to convey that I have conveyed to you that, we have these two libraries for testing of parallel code. There's sort of they represent different ends of a trade-off between how much do you have to write as a user and how much confidence can you put in into say tests that pass them. We have actually been able to find some bugs that were previously unknown, so trigger some nasty behavior in the new runtime. So some actual good old-fashioned torture. Yes. So if you too would like a friendly monkey chasing your OCaml 5.0 code around, you can have it, and there are OPAM packages there for you. I'll shut up now.
Thank you.